I invited my graphics class, but I didn't expect many of them to show up because I canceled class because this was the time that worked well for everybody to do it. So, um,
Extra credit.
well, the class at 2, I had to cancel it because we needed time.
Yeah.
So I couldn't really make it extra credit because they might have class at 1, in theory, right?
Okay.
This weird. I
does
needed
it show that
to
it's
cancel
recorded?
class so we could talk about it. I always feel like it's hard to get. I don't know. It's hard to get people to go to all these. It's hard. It's hard for me to go to them. All to all the other students.
How can I get rid of this thing? Oh, here, there we go. It goes.
Hey,
Hi, Professor. Okay.
so,
I see some people like this one. I'm not sure who are they. Should I accept them
I
or
don't know. I haven't had that much bad luck with random people joining.
yeah, it doesn't.
Setting us up like for these events, set us up as like Zoom.
Right.
Yeah, I set up the waiting rooms.
We
too,
had to
just-
do it on Zoom because Ricardo.
Yeah.
But
but I'm not sure who is this. I'm not sure. Should I accept it or I'm not sure.
Wow, you can include them right now.
I would just accept them. I can try to join in the meeting.
Okay, if you can, I can make you co-host also.
So let me join the Zoom meeting and then we can maybe get started. And then you won't have to worry about monitoring it. Since I've gotten this, did so much better luck with Wi-Fi on my old Mac. So surprised we went like I don't have phone.
Also, please help yourself with some of the candies and donuts that I brought, and also we have water here. Oh.
There we go. I'm joining. Success maybe.
So I
And then you might be able to right click on me. And,
yeah. Okay, now you're.
All right. So I guess I'll do a little introduction and get started. So go over. All right. So Soheil's been working with me for some years now and is finishing up. So he's done some work on distance judgments in VR, which has been something that's been my focus for quite some time. And I'm pretty excited about how he's looking at issue related to this that like people don't normally look at or people just kind of overlook and have overlooked for a long time. So I'll let him talk about this. I think it's gonna take you like 45 minutes, something, maybe. And then we'll have time for some questions and then the committee will meet. So I'll hand it off to you.
Thank you so much, Professor. Hello, everyone. My name is Soheil, and today I'm going to present my PhD defense dissertation about the impact of pre-experiment walking on distance perception in VR. This is a project I've been working on for a couple of years, and I hope you enjoy it. So first, as our motivation, the question is why our distance judgment is important for us. So there are many applications for distance judgment in virtual reality, especially. For example, we have training application and educational purposes if we want to train our students or some workers. For prototyping, for entertainment, for example, if we want to amuse audience to perceive virtual reality very realistic, we use VR, and distance is very important to basically give the realistic feeling to our audience to amuse them. As example, for a real world experience, some critical applications for distance judgment is military purposes. For example, accurately judging distance to virtual enemies or targets is very important for us. We don't want to make mistake here because realistically getting trained based on the situation is critical for soldiers. For manufacturing purposes, factory training on heavy machinery tools is basically essential. It should be safe to train these workers in VR, and having a realistic distance perception from those objects, from those heavy machinery tools is important. Another example is for sure for astronaut training, for practicing a spacewalk or reaching a tools, some sort of objects. It's very important. So they perceive distance correctly in VR. And also architecture or visual designers, sometimes they want to show to their clients how big or how's a simulated room or a 3D environmental of the building. So basically accurately understanding those distances is important for us. So usually distance is getting underestimated in virtual reality. For example, there are some studies that shows that for real world study, accuracy is above 90% up to 98% by previous studies that they have shown that if they do a distance perception study in real world. However, underestimation usually happens from 74 to 89% for virtual reality, from 1 to up to 20 meter distances. And there is a very good survey article by Renner et al. In 2013 that she provided a very good comprehensive study, and she found that more than 30 papers use direct blind walking in their studies, which I'm going to tell you about that in the next slides. So how do we measure distance judgment? We cannot for sure measure it directly, and there are usually two types of measurement. The first type is non-action based method, which includes verbal reporting. The reason that we call it non-action based because there is no action in that except just judging the distance and verbally say how far a target is. Usually it has its own issue, for example, unfamiliarity with the units. Some people use meters, some people use inches, some people use feet. Might cause problems for participants. An action-based approach, such as triangulated or indirect blind walking, such as blind throwing or direct blind walking, which usually getting used by other researchers. So our focus in this study is direct blind walking. So the question is, what is direct blind walking? So in direct blind walking, participants usually see the target on the ground. If they have VR, they're going to have a VR headset and the target will be show up in the virtual reality environment. But they can be also do it in the real world. So they see a target on the ground, and after they have a good amount of time to understand how far the target is and basically see a target, we're going to ask them to make them blindfolded. We're going to put the blindfold on their head, and when they said that we are ready, we're going to ask them to directly walk blindfolded towards a target until they feel like they're on a target. They might underestimate, they might overestimate, but where they waited exactly and stopped, we're going to measure how far did they walk blindfoldedly, and we rotate them, and we're going to put them back, and we're going to repeat this with different target distances and different objects. So it has its own pros and cons after using direct blind walking. So the pros of using direct blind walking, as I mentioned, Renner article shows that it's the most common method. There were more than 30 papers that have done this method. It's an action-based method, so the user doesn't have to deal with different units and our familiarities. And also it's accurate up to 25 meters. and it's easily reproducible for head-mounted display and virtual reality environments. However, it has its own cons. For example, it needs some sort of a pre-experiment procedure that need to be done for participants as a typical part of direct blind walking method, which we're going to talk about it. It has issue with counting steps. So the issue with counting steps is basically if participant count steps, they're going to have in their mind how far the target is, and they're not going to basically imagine they're walking or basically perceived walking while walking blindfoldedly. So we don't want that happen because that's similar to verbal reporting. We inform participants not to count their steps while they're like before doing the direct blind walking. So we do that informing participants. We need some sort of larger places to run the experiment because usually we're going to give some couple of more meter than the farthest target distance. So basically participants have enough place or enough larger room so they won't collide to any obstacles or any objects. So as we mentioned, direct blind walking needs some sort of a pre-experiment procedure called pre-experiment blind walking. We call it from now as acronym as PEBW. So people may be afraid of collision or walking unnaturally or basically deviate while they're walking blindfoldedly because we're not very familiar with direct blind walking unless we practice it. And most experiments makes participants to practice this direct blind walking prior to the experiment to get some sort of familiarization, to remove their fear or anxiety. And basically they practice walking for several minutes blindfolded with participants, and experimenter stops and turn participant before colliding to evolve. As example, if you assume that participants start walking blindfoldedly here, the experimenter is behind the participant, and when participants are blindfolded, assume they walk like this path. And as soon as experimenters see participant is about to collide to a wall, experimenters stop participants and ask them to stop. They stop. Experimenter rotate the participants and basically keep asking them to start walking until participants is getting comfortable feeling of blind walking. So this is called pre-experiment blind walking or PEBW basically. So, however, it has there are some issues with PEBW. For example, PEBW or pre-experiment blind walking is not a standardized or well-documented thing. We do not know how much about PEBW would influence or impact distance perception result because it's possible that it had some sort of effect on direct blind walking experiments. We do not know if we can compare these studies' results due to lack of consistency between their PEBW procedures. Some studies have done PEBW. So basically in this table, we have provided as some sort of summary from the previous research, from the recent research up to older research. And we found that in procedure of these researchers, sometimes they have not reported if they have done PEBW or not. So we put it as unknown because we're not sure if they have done it. Maybe they have done it, but it's not important for them. So they haven't mentioned it, or maybe they have not done it. And some people or some researcher mentioned that, but mentioned that, for example, for several minutes and did not mention the exact duration. And some other researcher mentioned they have done it, but they mentioned, for example, the duration, but not the size or how did they do pre-experiment blind walking procedure. So we were curious about the overall average of a distance perception result in these studies. And we can see this graph, there is almost around 5% differences between different researchers which have done the PEBW versus the researcher which have not, or we don't know if they have done it or not, or call it as unknown. So this discrepancy, we want to basically understand if it's going to impact them. However, for sure, we cannot compare these results exactly together because some of the studies work on different environments. Some of these studies mentioned, for example, like provided a VR room with different settings, different situation, different brightness, different objects, but it's kind of some sort of summary and motivation for us. The question is, can walking influence distance judgment? So some previous work shows that walking can impact subsequent distance judgment. So these studies usually manipulated the visual flow during a walking. And this kind of gives the experience of like discrepancy feeling for participants because of the mismatch condition between their visual speed that they're perceiving in their eyes and their walking speed. And related work that I'm going to talk about has usually three phases. The first phase is It includes pre-experiment distance judgment. Then they put participant in the condition of walking practice based on visually slower or visually faster condition. And then they do the post-experiment distance judgment to see how much this practice is going to influence them or impact them. We can see here for Reiser et al. In 1995, he did a very good experiment and nice idea. So basically, he had participants walking on a treadmill and kind of moved the treadmill by a truck, basically behind it. So he had two different conditions: visually slower condition and visually faster condition. For visually slower condition, the treadmill speed was more than or faster than the truck speed. For visually faster condition, the treadmill speed was lower than the truck speed. So these changes in velocity give some sort of discrepancy feeling to participants. For example, for visually faster condition, even though participant was they're walking for example, within 1.9 meter per second, but they perceive objects or targets getting closer to them faster. So this kind of gives them some sort of discrepancy feeling. And based on the result, they've shown that for visually slower condition, participants usually overestimate distance, and for visually faster condition, participants underestimate distance. Another study is by Moeller et al. In 2007. So she worked on the same exact idea of Reiser in 1995. However, she have done the experiment in a virtual big screen. So she had the treadmill, and basically she manipulated the treadmill, the visual flow speed in the virtual big screen, and she found the same result. There was overshooting happening for visually slower condition, and there was undershooting happening for visually faster condition. Another interesting result for Moeller was for visually same condition, which is basically the treadmill speed is similar to visual flow speed in the virtual object in a virtual big screen. There was 4% overestimation happen. So Moeller explained that there might be two reasons for that. First, walking on a treadmill is different than walking on a real world environment. Participants tend to drift forward using treadmill. And their second explanation is that participants probably look at a virtual long hallway, and that's going to give them some sort of objects or targets are getting farther from them than their actual distance. So they walked fast, they walked more than they should walk. Their explanation is not very clear, however, but that was their two reasons for this condition. Another important study, which was done by Fieldbeck et al. In 2008, and this is one of our main reference and critical study that we have used. So basically, he was curious about seeing the effect of blind walking versus normal walking for participants. So he designed a couple of experiments, and in his first experiment, he exposed participants to two different conditions with 3 minutes of walking. So in the first condition, he used with vision condition, which was normal walking, eyes open walking. And in the other condition, he used without vision or blind walking. Interestingly, participants tend to overestimate distance after they were exposed to blind walking compared to eyes open walking. And another interesting experiment he has done in this study, he was curious to see how does this blind walking impact participants. So he designed 37 successive trials of the blind walking, and over the trials, participants tend to overestimate distance. At the beginning, they underestimate, and over the trials, they started overestimating progressively. And they also progressively increased their velocity, which kind of interesting result, because it shows that after 37 successive trials, velocity also increased. Maybe they kind of adapted themselves, maybe they kind of increased their confidence. And it was a very nice research and experiment. So in this work, we have designed two experiments. So in our first experiment, we're going to answer, does PBW or pre-experiment blind walking impact distance judgment in VR? And if yes, how much or how does it going to impact? Does the duration going to matter? In a second experiment, we wanted to answer three different questions. Does the amount of eyes open walking prior to PBW matter in VR? Does excessive PBW cause overestimation in virtual reality? And how does walking with vision and HMD, call it see-through mode, impact distance judgment? So basically the new feature on new head-mounted display called see-through is some sort of a video camera output from the real world through the head-mounted display. We wanted to see the effect of that too, to see some sort of, if it's going to cause familiarization for participants. So our experiment description usually consists of several phases. First, participant arrive outside of our lab, then participant do 0, 1, or more loops of PBW around the hallway. Then we brought them into the lab blindfoldedly because we do not want them to see the real world VR lab. And we begin distance judgment experiment in VR. So in our first experiment, we varied amount of real world pre-experiment walking. So this is the hallway in air-free floor that we practice blind walking with them. So participants start front of the VR lab door, and basically based on their condition, if participants were exposed to 0 loop condition, we make participant blindfolded and directly bring them to the lab and start the experiment. If they had 1 loop condition, they would we blind them and basically ask them to walk blindfolded around the hallway for 1 round. And for the other 2 conditions, 2 rounds and 4 rounds, we practice them 2 rounds or 4 rounds of pre-experiment blind walking. So we had 72 participants in total, and 26% of our participants had no VR experience before. And this is the blindfold headset that we use for pre-experiment blind walking procedure. So for the pre-experiment blind walking, these are the 4 sides of hallway that we have used. The hallway length was 73 meters by 2.3 meters wide. And basically, we did not want participants to see the real world lab because some other studies shows that seeing the real world VR environment will impact participant result. And it took about 2 minutes for a participant to complete each loop. For example, it means for 4 loops of PBW, it probably take about 8 minutes. And this is the Oculus VR CV1, and these are the markers that we use to track participants based on the tracking system, external tracking system that we have used, Vicon tracking system. And we played a white sound noise to basically prevent participants to get hint from sounds of the environment and use them as a landmark for the direct blind walking trials. And this is our virtual environment. Targets is showing up for participants in different distances. And there were 17 direct blind walking trials, and we had 2, 3, 4, and 5 meter distances that repeated randomly 3 times, all of them. We also added several dummy trials, so 2 dummy trials at the beginning and 3 other dummy trials randomly along the 17 direct blind walking trials to prevent participants from memorizing where the targets are. And these dummy trials help to prevent memorization of the target distances for participants. And our result was interesting. So we have found that participants who were not exposed to any PBW or pre-experiment blind walking, they underestimated a lot compared to participants who had 4 rounds of pre-experiment blind walking procedure. So it shows that almost there is 20% differences. So the x-axis shows the target distances and the y-axis shows the walk distances, direct blind walking distances for participants. And we average all of participants in each condition and each target distances. And another interesting result shows that 2 loops and 1 loop, they're not significantly different from each other here. As we see, there are many much overlap here. And in the right graph, this is showing the same thing. However, for y-axis, we shows this walk distance percentage, and x-axis is just target distance. So we have kind of calculated the repeated measure mixed ANOVA, and it shows that there is a significant differences between conditions. And there was a significant main effect of target distance and walk distance also, because we kind of assume that it's happening because target distances are varied from 2, 3, 4, and 5 meters, and participant response kind of makes sense that it should be varied. And there was a significant interaction between target distances and conditions also. So we were curious and did a postdoc to see which conditions are significantly different from each other, which pair of conditions. So all of the pair of conditions were significantly different from each other, except 2 pairs. 1 loop and 2 loops were not significant from each other, as we see 1 loop and 2 loops kind of overlap themselves. And 2 loops and 4 loops were not also statistically different from each other. We were also curious to see some sort of a similar result with fieldback. So we kind of showed participant result percentage walk distance over the trials. So we wanted to see how participants adopt their walking distance over the trials. And we found that participants for 0 loops, they kind of progressively start start increasing their response, their walk distance. And participant for 4 loops of PBW, they kind of stabilize their result and their performance stayed consistent. So we kind of think that there is a possible similar effect of blind walking practice for zero loop conditions, because these participants did not have any practice of blind walking, and maybe the direct blind walking trial kind of act for them as a PBW practice. So they kind of, that's the reason they kind of progressively increase. But for these conditions, participants kind of stabilize the result, which kind of interesting because we believe that they might have exposed to PBW enough, so their result is consistent over the trials. So as a discussion and a conclusion, we found that pre-experiment blind walking significantly impact distance judgment. The changes in performance may be due to familiarity and adaptation in blind walking task. PBW effect can also have a calibration effect without visual feedback. We believe that it might be similar to visually slower condition in Moeller and Reiser paper, because in visually slower condition in those 2 other papers, participants basically walk slowly. Participants basically walk, but they perceive that targets getting closer to them slower than their walking distance. In our condition, blind walking, pre-experiment blind walking, participants do not see any feedback, do not have any feedback from their environment. So basically, even though they walk, but they do not perceive anything getting closer to them. So we believe that this is extremely visually slower condition. This can be similar to visually slower condition, however, without feedback. We also found that 4 loops of PBW is very close to 100% accuracy, and experimenters should definitely report the details of PBW, such as duration, size of the place, and where the PBW is getting practiced. However, the experiment 1 had some limitations. So we haven't captured some potentially valuable behavioral data from our participants. As we see in Reiser paper, he captured velocity over the trials. We haven't done that. And some important information such as velocity and how many times participant turned over each loop of PBW would also kind of shows or reveals some hesitation and anxiety in our participants. So we haven't captured that, unfortunately. So that's one of the reasons that we have designed another experiment called experiment 2. So in experiment 2 has a similar conditions as a similar situation as experiment 1. However, we have added 4 different conditions. We have designed 1 loop of PBW or 1 PBW loop as our control condition. The reason that we choose 1 is because in a previous experiment, we have shown that 1 loop of PBW is not significantly different from 2 loops. So we go with a shorter distance. We are also curious about seeing how does eyes open walking prior to direct blind walking practice or PBW going to impact participants. So we designed 8 loops of eyes open walking followed by another PBW loop in our second condition. And we were also curious about seeing if excessive PBW is going to impact overestimation. So we designed 8 loops of PBW. Another feature that MetaQuest Pro has is see-through mode. So basically in see-through mode, participants see the real world environment through the camera in their screen. So we were also curious, maybe that familiarization with VR, even though they're seeing the real world environment through the VR headset, is going to impact participant results. So we designed 8 see-through loops, so 8 rounds around the hallway, but they're with their eyes open through the head-mounted display. We had 64 participants, and all of them had normal visual acuity, and 20% of our participants had no VR experience. So for our pre-experiment conditions, so this time for this experiment, we have completely redeveloped our VR program. So previous program relied on external tracking system and OpenGL to kind of build up the virtual reality project. However, this time we moved completely to Unity game engine and redesigned our VR program. And also we removed external tracking system need. So we only relied on the embedded tracking system and embedded computer inside the virtual reality head-mounted display, MetaQuest Pro. So it has its own embedded tracking system. It has its own camera, so we do not need any other external device. Plus, we can use this device outside of the VR room in the hallway. And white sound noise was also played during a pre-experiment procedure. So this is a screenshot from the video see-through mode from participants, what they see in the 8 see-through mode when they have VR headset. And the time to complete per experiment procedure for 8 PBW loops kind of took 15 minutes. For 8 see-through loops, it took about 5 to 6 minutes. And for practicing pre-experiment blind walking, we kind of make the headset black screen, or make the screen of the headset blank. So we have also side blocker for the headset. So we, as you see here, this is a MetaQuest Pro that we have used. This is one of our participants that we did a direct blind walking trial inside a VR lab. We did not use this tracking system, external tracking system, and everything is inside this headset. And we have kind of ambient light and some sort of infrared light to help the tracking system work properly, because they need some sort of light in order to work properly. And the tracking system and the device recorded instantaneous positioning data such as XYZ and timing data, almost 70 FPS, or frame per second. And this is our simulated virtual reality room that shows the target distance basically for our participant inside the VR Quest Pro. This is a screenshot of that. And the result was also interesting for this one. So this is the same graph as experiment 1. The x-axis shows target distance, and the y-axis shows distance walked based on meter. And we have shown that participant who exposed to 8 rounds of PBW loops, they slightly overestimate distance over the target distance basically. And for the other 3 conditions, interestingly, 1 PBW loop as a control condition were not significantly different from 8 eyes open loops followed by 1 PBW loop. And also 8 see-through loops kind of had a similar impact, slightly a little bit bigger than our control condition, which kind of interesting because participants were not exposed to any pre-experiment blind walking in this condition. So we kind of did a statistical test, and we did a repeated measure mixed ANOVA test, and shows that conditions are significantly different from each other. So we did a post-hoc test for these conditions, and the only conditions that are significantly different from all the other conditions were 8 PBW loops. However, for the other conditions, they were not significantly different from each other after we did the post-hoc t-test. There is a main effect on target distance, on walk distance, as we expected, because target distance are varied, and also participant response would be varied. And there is interaction between target distance and conditions. Again, we show the performance over trials. So interestingly, we have found that for 8 PBWs, participants still getting progress over the trials in their walk distance percentage. We thought that we kind of hypothesized previously that maybe if participant had enough exposed to pre-experiment blind walking procedure, their result would be stabilized and they would be more consistent. However, this result shows that it's not still consistent, and participant can have overshooting effect, and which kind of shows us that there might be a peak effect, which optimal PBW might have a consistent result, such as 4 loops, but too little or too much PBW might increasingly change distance judgment result over the trials. And 8 loops might be overly boosted participant confidence. Another interesting result is the other 3 conditions acted similarly over the trials, and participants adopted themselves. So since we captured essential participant positioning data and timing data, we could kind of shows how participant would walk during a PBW. So basically, each point shows each frame positioning data for that participant headset on their head. And we calculated instantaneous velocity during a PBW. So these color, basically red color shows participant had velocity less than 0.3 meter per second. Yellow means participant had velocity between 0.3 meter and to 1 meter per second. And green means participant had the velocity from 1 to 1.5 meter per second. So this is the data that we collected from one of our participants during 1 loop of PBW as a control condition. So since in a previous experiment limitation, in experiment 1 limitation, we were curious about the number of loops, the number of turns that they had during a PBW, we also calculated that. So we made a computational program that count the number of turns. So our computational program consider 2 factors. The first factor is if the turning angle is bigger than a threshold, which is 10 degree, that would satisfy the first condition. And another condition is participant velocity during a PBW should be less than 0.3 meter per second. So we do the intersection between these two conditions, and we found these points here. We have also had a manual turning point. So we designed a manual turning point for the experimenter. So whenever they see participants are turning, we push the button. However, due to human error, we prefer to use only computational program, even though we kind of verify these points and they are mostly more than 95% correct. So since we have captured velocity during a PBW, we could calculate the velocity of 99 percentile velocity of participants overall average during each loop of PBW. So we haven't used average velocity because these average velocity usually includes a slow velocity at the beginning and also a slow velocity at the end. So we don't want to calculate that. So that's the reason we use 99th percentile velocity. We have also not used maximum velocity because due to possible tracking system error, maximum velocity would not be a good idea, even though we didn't see or observe any weird tracking system issue. We prefer to go with 99 percentile instantaneous velocity and average them for each participant over loops. And the result is interesting. So after calculating that, we have shown that participants increase their velocity, their 99th instantaneous velocity over the loops. So this kind of shows that maybe velocity increased because maybe participant had fewer turns after each loop. And the good news is we have captured number of turning points for participants in each condition. And we also see that over the loops, participants' number of turning point during a PBW kind of decrease, which kind of shows us there might be a possible effect. Maybe participants walk more straightly, maybe they feel more comfortable and adapted themselves and increase their confidence. We have to mention that we don't believe that it's going to, after, for example, 8 groups, it's going to increase because at some point, due to our walking velocity limitation as human, we're going to stabilize our velocity. But this result is interesting due to showing confidence. So fewer turns, as we see here, means walking more straightly, faster velocity over loops, and maybe shows more confidence due to building a trust in blind walking practice over the loops. I have to also mention that I didn't show HC through loops because in HC through loops, participant did not do any pre-experiment blind walking, so they're not blind walkingly walk basically. So we just show 3 conditions because that other condition is different than these 3 conditions. So similar to pre-experiment, we have captured essential data from our participant during the direct blind walking inside the lab. So we have shown the target distance and it shows how straight participants walk. And the same color shows the different velocity over the direct blind walking trials. So we wanted to confirm everything is correct and also capture velocity. And because of that, we could calculate velocity over target distances. So we used 99th percentile velocity meter per second over target distances. And interestingly, again, 8 pre-experiment blind walking loops is different than the other 3 conditions. Another interesting result in the left graph shows that participants usually have faster 99th percentile velocity on farther target distance compared to shorter target distance, which kind of shows that maybe they have enough time in order to reach their 99th percentile velocity for target distance, or maybe they are more confident in order to walk farther. Another result is we were curious to see how participants' velocity would change over the trial, similar to what fieldwork shows. And we found that over 17 trials, participants' velocity for 8 PBW is different than the other 3 conditions, and participants kind of increase and adopt their velocity. So we were curious about these spikes and these valley here, and we kind of plotted the data. How did we randomize target distance over these trials? So we believe that maybe because of this factor here that velocity got increased for farther target distance, since we randomly distributed target distances over the trials, maybe for these specific trials, there might be overall average farther target distance that happened. So maybe that's the reason participant had some sort of these spikes. However, it was partially correct. It was, for example, correct for trial number 7 and correct for example, for trial number 12. It shows farther target distance average or shorter target distance, but it was not completely explained all of the jumps and low valley points. So since we had positioning data from our participant, we had their y-axis information, which kind of shows their height. So we had designed a signal processing program to calculate where participants put their steps down and put their steps up. So basically, this is the height data from our participant, which is y-axis data from the head-mounted display. And basically, these kind of sinus shape tracking system shows that during these low points or local minima, where participant foot hit the ground in each step, and also these local maxima as a peak shows where the foot is lifted. Because when we usually do walking, we kind of have lowest height when our steps is down, and we have our highest height when our steps is up. We're not saying it's 100%, it has accuracy, but still it can have a good representation from our participants. In order to confirm these results, we did the manual calculation for a couple of participants to confirm that whether this data can represent stepping down or stepping up, which was correct. So because of these data, we were curious about step size, because usually we walk faster when our step size is bigger, and we walk slower when we have smaller step size, because it's not possible to walk faster with lower step size. It's usually we have that limitation. So we captured step size over target distances, and interestingly, the maximum step size for 8 PBW they usually have more step size or larger step size compared to other three conditions. And for farther target distance, again, their step size got increased. Maybe we hypothesize, maybe during a PBW, the reason that they have faster velocity, maybe they have larger step size. So that's the reason maybe they walk more straightly with larger step size and more confident, and more adaptation happen over there after exposing to extreme amount of peer experiment blind walking loop. So maybe that can explain. So it shows an interesting result for the relationship to velocity. And we have shown that AC through loops is similar to the other three conditions again, and confidence might increase participant step size for 8 PBW. So as overall view from all of the graphs that we have, we see that clearly 8 PBW loops is different than almost all the other conditions, and other three conditions usually has a similar result compared to each other. So for a discussion, we have shown that more PBW will improve participants' accuracy and consistency, and it will reduce their underestimation. We have found that 8 PBW had slightly caused overestimation on participants' result, and velocity, number of turns over loop, and also their step size are usually larger and bigger for this condition, and confidence and adaptation might get increased, and also less participant might experience less anxiety due to experiencing more PBW. For 8 see-through loops, we have found that it had a similar effect as 1 PBW loop, which in almost all conditions. So we have two explanations for that. Maybe they are more familiar with VR, they get more familiar with VR headset before the experiment, because they use the headset on their head and they see the real world environment in front of them. And maybe that gives them some sort of experience of familiarization and build some sort of trust in participant. Interestingly, personally, after I finished the experiment for some of my participants, they would, in this condition, some of them, when they took the headset out and they see the real world lab, which is not similar to the virtual world lab, they got surprised because they would see the similar real world. And we believe that maybe that happened here. And it kind of built a trust into a procedure of the experiment by seeing the real world through the head-mounted display. So they see that nothing is front of them. Like basically the virtual hallway is very long and large, and basically that kind of built trust in them. It can be a very good replacement for doing one loop of PBW, because it's usually easier to do 8 see-through loops, because we do not need any experimenter to do the pre-experiment blind walking, because participants they're not blindfolded, and they basically walk normally. They do not need any proctor or someone who can take care of them during a PBW. And also, so it does not need any experimenter to adjust participant blind walking practice. Another interesting result, we have shown that eyes open walking prior to PBW will not significantly impact participant distance judgment result. The possible explanation is we believe that doing one loop of PBW will kind of neutralize the effect of eyes open walking. And also participant or all of us usually use our eyes open when we are walking normally. So it's not something that we experience differently. And maybe that's the reason the result is not different. And it does not build any trust into the experiment because participants do not use a headset on their head and they do not see the real world environment through the headset. They just see it through their eyes, which is kind of it might cause that it's not having a different result. So as a conclusion, we've shown that VR researchers should inform details regarding their pre-experiment condition. Too little or too excessive PBW will significantly change distance judgment result. The amount of doing PBW will depend on the experiment. Some researcher maybe wants participants to have more accuracy. They might want to do more PBW loops compared to some participant. Maybe they are limited in their time of their experiment, so maybe only one PBW loop matter for them. And using a see-through mode in modern VR head-mounted displays such as Quest 2, Quest Pro might be a good replacement for doing PBW for experiment which works with direct blind walking. And however, our experiment has some limitation. We just still do not know how does PBW will impact direct blind walking in other environments such as real world and augmented reality. Fieldwork have shown some sort of result for the real world. However, it was not as deep as our study. There might be more effect of see-through walking on augmented reality version of distance perception because since we have shown that participants have basically similar accuracy to one loop of PBW, maybe when they were exposed to augmented reality version, they kind of see it's a real world, so they will not worry about walking blindfoldedly. And it's still interesting to do other types of distance perception methods, such as indirect blind walking or blind throwing, to see whether PBW has impact on them. And replication of see-through result is necessary because for the first time we have shown see-through result can be a good replacement for PBW, and confirming our result in a different environment and from a different researcher would be essential. Yeah, in a summary, we have shown that PBW matter, both insufficient and excessive will distort result, and documentation about PBW is critical, and increased PBW associated with faster velocity, larger step, and fewer turns, indicating growing confidence and adaptation. And thank you so much.
All right, so first, any questions from not committee members?
Also virtual
Yeah,
attendance, if anybody has question.
I think we should be able to hear people on Zoom
Yes.
as they talk. Are there any questions?
Sure.
Well, nice talk.
Thank you so much.
So I missed the first part. So especially in one of the slides, you showed that there was no statistical or difference between one PBW and two PBW. What would be the reason for that?
Based on the results, basically. So basically, when participants are exposing to one PBW loop, they have less duration. You said it's not the different, they do not have a different result.
That's what I thought you said, but
Yeah. So basically,
wrong.
but we believe that maybe some certain or threshold of doing PBW, such as one loop or two loop, did not had the same effect and did not significantly change, because we believe that doing certain threshold might kind of stabilize participant response, but too much or too little would distort the result. So that's the reason we believe that maybe one loop and two loops kind of in that stabilized threshold, in that kind of duration. And that's the reason it did not impact participant responses. That is our explanation. And two loops and one loop is usually during the duration, which other researcher shows about 2 minutes to 5 minutes of pre-experiment blind walking. Does that answer your question? Thank you. Any other question? I would be happy to answer.
One more question. So
Sure.
what are the practical applications of your findings? So basically you're saying you can replace PBW by those new VR sets. Is that what it is?
Yes, we believe that it's possible to use see-through mode, which is a video see-through camera from the real world environment through the headset. So this new feature was added into newer head mounted display that they could see the real world environment. We believe that it's possible to replace it because there maybe participants get more familiarization with working with VR headset, and then they get less anxiety working with VR headset, and that's a reason. However, it's still important for other researchers to confirm our result because this is the first time we have used these kind of features and information or data collection to show our explanations, our conditions. You're welcome. Any other questions?
Any other questions, either online or in here? All right, well, so thank you for the presentation. So I think, guess we have the public leave, the committee stays, and the committee has their questions. So thank you, everybody. And I guess there's food over there.
There is
too,
food
so
over here.
yeah,
Please
maybe
help
have
yourself.
food,
Yeah.
so There's less leftovers.
Let me start the recording.
Yeah, so usually we probably just stop the recording and then probably have other people leave.
Yeah, I can do that.
And Ricardo. Probably.